Now, yesterday we got the electrolytic cells. You guys are going to be doing that same electrolytic cell. I'm going to move the camera, show it to you. People who are at home. Anybody at home here? No, they're all here. Yeah. But either way, we're going to use that electrolytic cell. I have it set up. I know it's kind of in your way if you're on that side of the room, but there's nothing else I can do because it's so old, as you can see. That's the first one I had. That's at least 30 years old because it was here when I got here. And I bought other ones over the years, but nothing works as well as that one. Also, the other ones have broken and they're too small. I mean, there's 1,000 reasons why that's the best one. And our results from this demo are going to be very good as well. We're going to learn how to not just diagram an electrolytic cell, but how to do calculations with it. We're going to actually do some calculations with it. We're going to be able to predict how much. Remember, this cell right here is equivalent to the aqueous sodium sulfate cell, the last one we did, where you had hydrogen produced at one electrode and oxygen produced at the other. All right, you'll see that in a minute. Well, actually, in about 15 minutes, because I'm going to show you how to do the calculations first. So this is equivalent to that cell, that electrolytic cell. And I'm going to not only be able to diagram which is the anode, which is the cathode, which is positive, which is negative, and all that stuff. I actually am going to be able to predict how much hydrogen or how much oxygen is produced from that decomposition, from that reduction of water. Okay? So we're going to do some calculations as a series of conversion factors. Now that's good because I first taught you how to do conversion factors back in Chem 1, Chapter 2. I mean, it was one of the first things we did after we learned about the scientific method. All right? And because I knew it was going to be important. All right, we learned how to do conversion factors. I taught you how to do conversion factors using metric conversions, grams to milligrams, kilometers to meters. We did that. Not because we had to, not because it's easier to do kilometers to meters by a conversion factor, but because I knew this was coming. This is going to have a conversion factor longer even than stoichiometry. Stoichiometry had like 2, 3, sometimes even 4 conversions. This guy's going to have even more than that, as you'll see in a minute.
Awesome.
All right. Well, you got to know some terms here in order to do these calculations. And basically, it all boils down to this. I think the best way I could explain this is trying to get from chemistry to physics and how we do that. And the guy who came up with that was Faraday. All right, he realized a simple law. Faraday's law says that the more electricity you put through something, proportionately, you're going to get more reduction. All right, so it's basically a very simple law. It's proportional to the amount of electricity, the amount of reduction you're going to get. And so there's a lot of these. One of the units that's named after Faraday, Faraday, is the amount of electricity it takes to reduce or oxidize one, I say, equivalent weight of a substance. In effect, that's 1 mole. In effect, but not exactly, and I'll explain. Just copy that down. See, Faraday's working on the chemistry side of this, and then I'm going to talk about the physics side, the Schrader side of it, and then we're going to put the two together. Somehow there's got to be a link between them. You can see why this is the chemistry side of it. We're talking about, there's a number we're familiar in chemistry with, right? That's the amount for 1 mole. 6.022 times 10 to the 23rd electrons, 6.022 times 10 to the 23rd atoms that have undergone oxidation or reduction. All right, that's 1 mole of that. So why not just say 1 Faraday is 1 mole? Well, because, here's why. Say I've got a guy like, I'm going to use him as my example, I think, later, zinc. Zinc has a +2 charge. Don't write this down. If I want to reduce zinc to zinc metal, down to its elemental state, how many electrons does it take? 2. It takes 2 electrons. All right, not just 1. So 1 mole of zinc is going to take 2 moles of electrons. That's where equivalents come in. We've seen this before. Like, for example, a 1 molar solution of HCl and a 1 molar solution of H2SO4 are not equivalent, right? Why? Because he's got twice as many H's to donate to make hydronium ions, right? So, what's an equivalent? How are they related? Well, that's where we need another conversion, another term, another way to do this. Basically, equivalents are the same as moles, except you multiply by the number of electrons that have been used in the oxidation or reduction process per mole. So a guy like zinc would have 2 equivalents per mole. You may remember doing this in the acid-base chapters. I would think you did. Remember talking about equivalents. Matter of fact, we had to do that even in the titration examples. NaVa equals NbVb. I had to use N, the normality, because molarity wasn't good enough. Normality took into account the equivalents per, acid molecule, how many H's there were per, or how many OH's per base molecule. That's why we used NaVa, not just MaVa. All right, well, we're still in chemistry here. Equivalents, moles, 6.022 × 10 to the 23rd, all of that is chemistry. Let's talk a little physics now. If you're in physics, and the only one in here in physics is Jesse, but if you're in physics next year, some of you are taking the AP E&M, you will find, I'm sure somewhere along the line, maybe I'm wrong, the word Coulomb. Have you heard about coulombs yet, Jesse? Yes. All right. Coulombs are a physics term. It's basically, I'm not going to go into it. It's not important for chemistry. It's the unit of charge. Kind of like grams are the unit of mass. Liters are a unit of volume. Coulombs are a unit of charge. That's how you measure charge, a coulomb. Okay? And here's another physics term for you. Again, remember, our goal is to relate chemistry to physics in a minute. Here's another physics term for you. It's not coulombs are unit of charge, but it's much more useful to talk about how many units of charge are going past a certain point per second. All right, so that we call an amp. 1 amp is a coulomb per second. That's the flow of charge, and it measures current. Tomorrow I'm going to do a little analogy on how current and voltage are all analogous to water. All right, I don't want to do that today because this is a longer class than I thought. The other class I tried to do them both, and it took too much time. But tomorrow I'll do a little analogy on that, and you'll understand what I mean by current. But basically, current is a flow. It has the same word, flow. All right, current. You think of that for a stream, for water. You think of it also for the flow of electrons or the flow of charge. All right, so physics terms. Amps, coulombs, chemistry terms, moles, equivalents, 6.022 × 10 to the 23rd. How are they related? By this simple factor. 1 Faraday, that's chemistry, equals 96487 coulombs. That's how we're related. Okay? And knowing those, I can convert. Here's the reason I want to know that after you write that down. In physics class, you want to know about a light bulb, or you want to know how much work you can get out of a motor or something like that, and you want to know what the resistance and all this other nonsense is. That's great. You can all hang out and hear these amps and volts and all that nonsense. But if you want to know something useful, like, for example, how many grams I can get from, or how many milliliters I can get from a reaction when I'm trying to reduce something or oxidize something, then I got to use this. That's the way to link the two together. All right, let me show you how we're going to do that in a couple of examples. Ready? Copy this guy down first.
Who needs physics?
Exactly. This is why I said, though, even to the Chem 1s who are signing up for classes this year, Chem 2 is a good class to take if you're taking AP Bio or Bio 2, because the first half of the year we did a lot of biochem, a lot of organic. It's also good for physics because in the thermodynamics, that's actually a physics. If you take physics, you could take thermodynamics as an entire chapter. Electricity, redox reactions. I mean, there's a lot of overlap between these two. That's why I recommend. Unfortunately, there's a couple of kids this year who signed up for AP Bio and AP Physics, which I don't think fit together a lot. There's no crossover there at all. But I'm not going to tell you.
That's what I did.
You did for next year?
Yeah.
Oh well, you've already taken Chem 2. But I'm saying people who hadn't taken Chem 2 yet, it makes more sense for them to do that.
You're just going to make yourself. It's going to make college easier. I don't think so.
Well, I don't know about easier. It's
Well,
not gonna make next year easier, but that's all right. No, it's actually I'm not. It wasn't about you should challenge yourself. It was about the fact that people who hadn't done it. It's the best. It's always I think it's best to take Chem 2 matches better with either the bio or the physics. Whereas there's no overlap between AP Bio and AP Physics. There's just none.
Wait, so you take AP Bio?
So
Told
anyway.
kids not to take Chem 2 and they didn't listen.
That's right. They just didn't listen enough. All right, now here, first thing I'm going to do here, and you should do this with every problem, is you're going to have to write down the guy who's being changed the way they want. It asks about reducing aluminum chloride. So you got to write that formula correctly and see how many equivalents there are, what the charges of these guys are. Aluminum chloride looks like this. He's Al with a +3, Cl with a -1, AlCl3, right? Write that down. So if I'm going to reduce somebody to their elemental state, 0 charge, who would be the guy who's being reduced? The aluminum or the chloride? The aluminum, yeah, because he's going to have to go from Al with a +3 to Al with a 0, and that takes electrons. That's what reduction means. Reduction means you're adding electrons. How many electrons am I adding? Everybody agree I'm adding 3?
Yeah.
See that? Okay. So that's going to be important. The reason I want to write that up there, it's going to be important for my conversions in a second. All right, now you want to start way over to your left because these conversions are going to take a little while. This one's not that long. The next one's even longer. What do I do in any conversion? If this question is said, ignore everything else up there. You know, and it gave you 2 grams and you want to convert to kilograms. It's the same thing. You always do what first in a conversion? You write down what? The given. 2.0 moles. Because that way, even if you're a little confused, and you will be in these, I'm sure, at times, you know you're going to have to put moles on the bottom. All right? Moles go on the bottom. Now, what are moles related to? Well, we have to take into account the equivalents, don't I? Right? How many equivalents are there per mole? I want to go to equivalents. How many equivalents are there per mole? 3. Okay? 3 times as many moles as you'd expect because he's got a +3 charge and I got to use 3 electrons per atom, per ion. All right, good enough. That cancels out moles. Now, let's look back. And the reason I want to do it, watch, this won't erase it. I'm just going to go back to this again. Okay? These are all our terms we can convert to, right? I am now in equivalence. I've got to get to a physics term. Okay? The link is Faraday's, right? How are Faraday's related to equivalence? They're the same. 1 Faraday is basically 1 equivalent weight. All right, and you're going to get sick of writing this down because so many of these are going to require this same step. Come on. Equivalents go on the bottom, Faraday's on the top. 1 Faraday contains 1 equivalent. It seems silly to have to do that, but that is the relationship. All right?
So it's like stoichiometry.
Yeah, it's kind of like stoichiometry. All of this is, you're doing conversions.
1 farm.
All right? Now, I'm in Faraday's, and I want to get to coulombs. Again, can you look back here and see where you're going to go next? Are Faraday's related to coulombs in any of these? Sure, right down there, right? So how am I going to write this? Well, it's pretty easy.
This is too easy.
I know. Faraday's in the bottom, coulombs in the top. 1 Faraday contains 9, 6, 4, 8, 7 coulombs. Do your math. And what do you get?
No wonder we do so
Does that say Al +3 Cl?
Al +3 plus 3 electrons.
On the top right.
Oh, AlCl3. That's aluminum chloride.
Come on, Holden.
I couldn't read it.
You're in Chem 2. No.
Shut up, you guys.
Okay, what'd you guys get for that?
5.8 times 10 to the 5th.
Okay, right. That's right. Or you may, if your calculator keeps it in standard notation, 5.80000 coulombs. Or 5.8 times 10 to the 5th. Everybody get that? All right. Not bad. Simple conversions. But that's not a very useful calculation. Let's do one that's going to ask me a little bit more useful thing, like this one here. And it's also going to get us ready to do that guy right there in a minute. Okay? Copy that guy down.
Guys, this one will be more useful. Wait, the camera's still on.
What do they do?
Copy? Same thing, I got to write the equation down for what's happening. It tells me I'm reducing this. So you should write the equation of what's going on with the electrons. Okay? Well, it says zinc with a +2 charge, zinc solution, and it wants to know you're getting zinc metal out of it, Zn with a 0. That takes 2 electrons. So yeah, it's going to be important when we go from our equivalents to our moles to equivalents. Okay. Now, this one, I really need you to start way over to the left and write small. Because actually, I'm going to have to erase a little bit because it won't fit on my whiteboard here, smartboard. All right. Here's the thing. You're given, and this is often confusing for people. I'm saying this right now. You write down, okay, I know I got to write down my given information. Okay, it's 25.0 amps. And then I look at that board from a little while ago, and I got a problem. I don't see anywhere where you're going to put amps on the bottom. And well, there's a reason for that. Amps are another name for what? Coulombs per second. So I can simply rewrite. I can simply rewrite 25 amps as 25 coulombs per second. Okay. 25 coulombs per second. And it's 25.0. Again, I'm trying to save as much space as I can because I know I won't have a whole lot of room here. All right. Now, what do I want to take care of first? There's a whole lot I can go to. I can start doing the electricity calculations first, but I like to take care of the time element first. You know, I didn't just have this guy going on for 1 second. Otherwise, I could have used that 25, right, as it is. I had him going on for 10 minutes. So I have to convert my seconds to minutes, first of all. Seconds on the top, minutes on the bottom. 1 minute contains 60 seconds. Seconds cancel. And how many minutes did I have? 10.0 minutes. So there you go. That's my time element is now taken care of. I'm in coulombs now. Minutes have canceled, seconds have canceled. I'm out of there. I'm in coulombs. That's nice. I want to get to moles. That's a useful thing. I want to know how much zinc, how many moles of zinc I'm going to get from this process. All right? Well, how do I go from If you just try to do it all at once, you're going to get lost. What do you think I should do next to get my coulombs into some chemistry unit? What do I want to go to? Well, here, let me ask you this, because it's often it's confusing. I told you, one of the beauties of doing this system as a conversion factor is you may be confused, but you know what units have to go on the bottom here. What has to go on the bottom? Coulombs. Why does coulombs have to go on the bottom? Because it's on the top up here. Now, what would be useful? I'm trying to get to a chemistry unit. I have a physics unit. I want to go to Faraday's. Yeah. 1 Faraday contains 9, 6, 4, 8, 7 coulombs. I know this is in the way, but I can't move it because it's very fragile.
Coulombs have to go on the bottom?
Because I have 25 coulombs per second. Coulombs are on the top of there. So I have to cancel. All right, so now I'm in Faraday's. Ah, that's good. What do I have to do now? I'm trying to get to moles. Well, Faraday's have to go on the bottom for sure. And what goes on the top? What are Faraday's related to? They're related to equivalents. All right, 1 Faraday is 1 equivalent, and that will be the case all the time. But what will not be the case all the time is equivalents to moles. Faraday's have canceled now. And I've got equivalents on the bottom and moles on the top. 1 mole contains how many equivalents? In this guy? 2, yeah. Because I had used 2 electrons right there. So 2 equivalents. Now I get my calculator out. I plug all that in. And I get a small number. What do I get?
0.0777.
Yeah, you actually get 0.0777 moles. All right? Well, look at that. I mean, you got 1, 2, 3, 4, 5 conversions. And the next one's going to have even more. Okay?
It has to be a partial credit or no?
Oh, absolutely. And you won't have to memorize this number either. I will give that number to you. You should know what all the other stuff you should know. They're basically definitions. Faraday is an equivalent. Coulombs per second are amps. All right, they're basically definitions. But this number I will give you. Okay. All right. Now I'm going to do the demo now. Now the demo question is going to be, I don't have it written down, but I'm going to just show you what we're actually going to do it. We're going to physically do it. So I'm going to move this around here and show you. Maybe I can put some books here to make it a little bit better. All right. Now, hopefully this works. This is my setup here. Maybe a little too high. Can you, oh, I know I can do that. There's my ammeter. All right, that measures the current. All right, and I'm going to turn this on. This is just basically like a battery. And I turn that on and look at the ammeter move. Oh, by the way, I also want to get my stopwatch out. And I'm going to hit it. I want it on for 10 minutes. Okay, so I'll put it on here, and I'll put it at 0.38, around 0.38. I don't want to move it. Now, you guys out there.
Yeah, that's how.
In the studio audience.
No, you guys out there can see these bubbles. Let me show everybody else the bubbles there. Okay, and we're starting to collect the gas up at the top. All right, those are the bubbles, and there's my ammeter. Okay, now I'm going to try to maintain, because it will change depending on the resistance and the water and everything, and these wires are, this whole thing's so old. I want to make sure to try to maintain that at about 0.38, and I will keep an eye on it every now and then to keep it at around 0.38 amps. And I'm going to also keep this, I want to stop it at exactly 10 minutes so that that's how long we'll have collected. Okay, that's your question. Okay, you're going to write that down as your question on the board. What's my question in this problem? You phrase it for me. What should I say? What do you think my question would be in this problem? I'm going to let that run for 10 minutes, and I want to know how much hydrogen gas is produced. What do you think? What's that? Same as the last one. How many? Well, not exactly the same. It would say pretty much, and I want you to write this down. So somewhere along here for your demo. Let's call it example 3 if you want to. Oops. Call it example 3. Don't write electroplating. Example 3. All right, call it example 3 if you want to. And just say how many milliliters of hydrogen gas are produced from passing, I'm going to try to keep that at 0.380, passing 0.380 amps of current for 10.0 minutes through water. Okay, so there's your question. Now I'm timing that right now. You guys start doing that problem. See how well you do. What's going to be different about this one at the very end? We know how to get to moles, but do you know how to get it to milliliters? That's a good question. And we'll talk about that at the end. So definitely get it to moles at this point, and you can stop there at moles if you want to, and then we'll see what we're going to do after that. See who remembers. In your class, they remembered both ways you can get the answer from this. And I was happy to hear that. Maybe you guys will too. We're about halfway there. Things seem to be going pretty well. Over here and sticking around 0.38. So this is an electrolytic cell. While you're doing this, this is exactly what you diagrammed yesterday and what you'll be doing in homework today in a minute. You'll be telling me which one's the cathode, which one's the anode. You'll be telling me, matter of fact, if you're in a minute, we're going to need to write the equation down for this. Why don't you look at what's happening at the hydrogen electrode back at the sodium sulfate cell? What's going on there? What equation is happening at the hydrogen electrode? Because that's going to tell you the equivalence per mole, isn't it? Look at what's going on at the hydrogen electrode for this guy, at the sodium sulfate one. Matter of fact, I'll write that with you right now, so we're not don't want to get the wrong answer here. You had water, correct? And what's he becoming? I'm asking about the hydrogen here. So he's becoming hydrogen gas. What else happens at that electrode? Does it say in this one? It becomes what? Look. What does it become? Is that it? H2O becomes H2? Look under sodium sulfate. Now. Yeah, why? Because it becomes, what does it say in the observations? It becomes basic. All right? So plus OH negative ions. You got to balance that at this point. So you need a 2 there and a 2 there. And to get everybody happy, what would you have to do? Add 2 electrons to make everybody balance the charge out. By the way, if you had just taken your H2, your H plus is becoming H2, it would have given you 2 electrons as well. So my guess is you probably know that there are 2 equivalents per mole either way, right?
I did the other way.
Yeah, that's fine. But this is the actual cell that you were diagramming. That's what it should have looked like. All right, now you guys know how, I'm just going to set this up real quickly. I hope you all got the answer. What did you get for moles at this point? 0.00 something? Anybody get an answer for this? 0.380 coulombs per second, right? Times seconds over minutes, 60, times 10.0 minutes, times coulombs in the bottom, Faradays in the top, 1 Faraday, 96487 coulombs, times Faradays at the bottom, equivalents at the top, 1 to 1, times equivalents at the bottom, moles at the top, 1 mole contains 2 equivalents. And you should be at that point right there, right? Everybody's at that point? Okay. We have about 2 minutes left on that thing. Don't try to remind me if I forget. How do we do that last conversion? Anybody remember? I could do more. You're right. There's a third way. I wasn't even thinking about that. I could go moles to grams and then use the density of hydrogen gas and do that. Good grams to milliliters. But there's an easier way. There's actually 2 other ways you can do it. Because first of all, I didn't give you the density, so you don't know it. What's another way? They came up with it. Come on, your class. That's good. You came up with a third one. That's good. But what's another way? Think of your gas law chapters from Chem 1. What did we use in Chem 1? What number related volume to moles? You know, 1 mole equals 6.0 to 2 times 10 to the 23rd. All right, 1 mole equals atomic mass in grams. What else did 1 mole equal? Remember the number?
For volume?
For volume.
22.4
for a gas. Right? Now, why? I mean, I'm going to have you guys do that, okay? Moles in the bottom, liters in the top, 22.4. And then you have to do 1 more conversion because you want it in milliliters. So it'll be like, I'm going to do it down here. Liters in the bottom, milliliters in the top. 1 liter contains 1,000 milliliters. All right? Do all of that and get an answer. There's a reason why that's wrong, okay? But it's not horribly wrong. There's a very small reason why that's wrong. Why is that? Why shouldn't I really be able to use a 22.4? What does that imply we're at? That we're at what?
Equilibrium.
Not equilibrium.
Right pressure.
Yeah, right temperature and pressure. STP. Remember STP?
Oh, yeah.
All right. Oh, you got 30 seconds now. All right, but either way, do all the math for that. What do you get for your answer for how many milliliters? Because this thing's going to be done in about 20 seconds.
26.9.
You got 26.9. Anybody else get that?
6.5.
Oh, 26.5?
I got 0.4.
All right, 26.5 milliliters. We got 10 seconds.
Rounds up, you jackwagons.
I got this.
Whatever.
A little bit more time here. 4, 3. Okay. All right, I'll let that rest of those bubbles rise up there. We should get 26.5. Now, by the way, while we're waiting for those bubbles to finish rising, and we'll look at that in a minute, what's wrong with that number? Well, 22.4 is at STP. We're not really at STP here. I can look up the pressure. What's the third way we could do this one? Instead of doing this conversion right here, instead of doing that, what could I have done? Gotten my answer in moles. If I got my answer in moles. But why don't we do that? See if we get which way we get a closer answer. Okay. Get your answer in moles at this point. Stop here. Tell me how many moles that is. It'll be a very small number.
I got 0.0012.
Yeah, I got
0.0012. Should be one more significant figure.
118. 118.
All right, 0.00118. All right. Who remembers what we could do if we're not at STP? What do we use? The ideal gas law. Remember? PV equals nRT?
Oh, God.
Yeah. I want you to do that. Let's see which one we get the. This was the answer for using 22.4. I don't know which one we're going to get the better answer for. PV equals nRT. You're solving for V. You need to know the temperature in the room and the pressure. Let me go look up the pressure from Schrader's room. He has it on the thing on the roof.
R is a constant.
0.0821 liters something per moles Kelvin.
Oh, that was the same as my bad.
What was that?
What? Hey, well,
Eraser?
are you doing anything after
Oh,
school?
okay. I don't remember.
Yeah, basically.
Balls.
Balls.
All right. The pressure is 29.73. I'm sorry. That's in inches. You're gonna need that in millimeters of mercury. Or actually, you have to convert that to atmospheres.
Oh,
So,
my God.
It's 754. 754 millimeters of mercury used for your pressure, which you'll have to convert to.
I've been 54 and there's 760.
Convert that to atmospheres. Your temperature in the room, it's going to be around 20 degrees. Just use 20 degrees Celsius, which you have to convert to Kelvin. Do that. Yeah.
0.99.
0.993.
Yeah, 74.
Yeah, how do you set the atmospheres?
Divide by 764. Millimeters of mercury.
That was 754 by 764.
Come on, do it.
Wow, we're trying. Let's go.
Look at the size of this problem.
It's dumb.
Wait, what was the temperature in the room?
20. Use 20.
20.
Remember, 20 plus 273. 293.
293 Kelvin.
293. Awesome.
Okay, so it would be.
What's N?
Let me,
N's how many moles? Wait, what's the R?
0.081 liters out. Liter or something per mole Kelvin, right?
what was my moles again? 0.00118?
Yeah.
This is what you have, okay?
Liters out.
20 degrees Celsius plus 273, which is 293 Kelvin. And your pressure, what did I say was 754?
Yep.
754 converted to millimeters of mercury on the bottom.
0.992.
Atmosphere on the top, 1 atmosphere contains 760. What is it?
0.992.
992. All right, use all that. Solve for V. You know, PV equals nRT. V equals nRT over P. What do you get?
28.6.
28.6.
Sure.
Okay, well, that's even worse because this is our correct answer. This is our observed answer was 25.1 milliliters. We figured out 26.5 using 22.4 at STP and 28.6 using this one. So I mean, but still, it's pretty darn close. And of course, last class we were like dead on. It all depends on, you can have some little leakages, which no surprise this would be a little low because you do have a little bit of a, you know, these could leak. You can also have the current isn't exactly right on this ammeter as well. Last thing I want to do is Dayton, you come up here. Come here, I need your help. You smoke, don't you? Come here. Yeah, here you go. Light this on fire for me. We're going to test to make sure what we collected. Get back away from me. What we collected was hydrogen gas.
What would you like?
Date, you pour back.
Dayton's a whack.
Hey, you're a smoker, right? No, don't get too much.
All right, bring it over here. All right, now you put that across the top of this test tube. You ready? This test tube in my hand. How you been? You good? Scared me. Good, very good. It's hydrogen. Good. We did the right side. Okay, blow that out. Run another water back there because you can't use this one. All right. So there you have it. Not this water. Don't use that one.
Put your
Lighter back. Uh-oh, you got smoke alarms going off here.
Now your homework is
It smells real good.
on page. How you doing? How you doing? All right.
The sulfur. How you doing?
Page 894. 894, 18, 20, 23. 23.
Thanks, Coach.
Thanks, Coach.